Hello everyone. Now I'll start about a chapter of class 11 chemistry, which is hydrocarbons. At first we'll start from the nomenclature, then to preparation, and finally to the reaction of the hydrocarbons. The structure of the groups: CH3, CH2, 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 and corresponding alcohol is CH3, CH2, 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 OH. The name of the alcohol is pentanol. The 5 carbon here is attached, so it is pentanol. Next, there is 5 carbon. The alcohol group is in 2 position, so the name is pentuol. And in the third example, there is OH group in the 3 number position, which is pentriol. So there are 3 isomers here. There are 3 positional isomers of this alcohol. Next come to a methyl substituent into butanol. So it is 3-methyl butanol. Next is 2-methyl butanol. Next come to 2-methyl butanol. Next structure has the name 2,2-dimethyl propanol. The next structure has 3-methyl butanol. The structure and the UPAC name with remarks. The first structure is given here. The numbering starts from the long carbon at the end of the long carbon chain, 1 2 3 4 5 6 given here. So there is 2 groups, methyl and ethyl group. So alphabetically, ethyl group, the name of the ethyl group will come before the methyl group. So it's the long carbon chain is actually hexane, so the name of the compound is 4-ethyl 2-methyl hexane. Next come to the second example. Here the long carbon chain is octane, and there is 2 groups, one is ethyl and another is isopropyl. So the name will be done after the numbering from 1 2 3 4 5 6 7 8 from the right side. So the name will be 3,3-dimethyl 5-isopropyl 4-methyl octane. Then the third example is Third example is 5-sec-butyl 4-isopropyl decane. Here the long carbon chain is decane. There are actually 2 sub chains, which is isopropyl and another is butyl. Butyl, not butyl, it is sec-butyl. So the name is 5-sec-butyl 4-isopropyl decane. Number 4, here the long carbon chain is nonene and the side chain is neopentyl group. So its name will be 5-neopentyl nonene, or its name can be like this: 5 next dash with bracket 2,2-dimethyl propyl nonene. Next come to the naming, which is heptane. So the alphabetical priority order, and there is 2 subchain, one is methyl, one is ethyl. So it is 3-ethyl 5-methyl heptane. From unsaturated hydrocarbon we can prepare the alkanes. If we reduce ethane with hydrogen in presence of platinum, palladium or nickel, ethene will be converted into ethane. Propene will be converted into propane. Propyne will be converted into propane. So it is full reduction or hydrogenation. From alkyl group we can synthesis alkane. Let's take chloromethane. If we reduce with zinc HCl, zinc HCl will generate hydrogen, nascent hydrogen, so it will reduce the methyl chloromethane into methane and HCl. Then similarly chloroethane will be converted into ethane, chloropropane will be converted into propane. From carboxylic acid we can synthesis by decarboxylation. The reagent is soda lime, NaOH, CaO and heat. So sodium ethanoate is converted into ethane. We can synthesis the alkane by electrolysis also. It will produce in anode. So acetate anion will be converted into methane by decarboxylation or anodic oxidation. The cathode and anode reaction is given here. Physical properties of alkane. Alkanes are almost non-polar molecules because of the covalent nature of the CC and CH bonds. Due to very little difference of electronegativity between carbon and hydrogen atoms, they possess weak van der Waals forces. Due to the weak forces, the first four members C1 to C4 are gaseous and C5 to C17 are liquids, and those containing 18 carbon atoms or more, they are solids, gummy solids. They are colorless and odorless. Next come to the reaction of the alkanes. First one is substitution reaction. Methane is subjected with chlorine in presence of UV light or sunlight. It will produce chloromethane, dichloromethane, trichloromethane or tetrachloromethane through chain reaction one by one. Mechanism. This is a radical mechanism reaction. The first will start with initiation, second propagation and third termination. Initiation will start with the breakage of the Cl-Cl bond, homolytic fission with H nu. The Cl-Cl bond will break into chlorine free radicals. Then chlorine free radicals will simultaneously will attack into alkane CH4. It will produce HCl and CH3 dot radical. Then CH3 dot radical will combine with the another Cl radical in the propagation process. So it will generate CH3Cl, CH2, Cl2, CHCl3 and CCl4 one by one depending upon the concentration of the chlorine. And finally in termination reaction, Cl-Cl radical will combine with Cl2 and CH3 dot radical will combine into ethane, and it will end up into the product. Next come to controlled oxidation. Methane is oxidized with oxygen in presence of red hot copper with pressure 100 atm. It will generate methanol. In presence of oxygen and in presence of catalyst M2O3 and heat, it will produce methanol. In presence of Mn manganese acetate, in presence of manganese acetate and heat, ethane and oxygen will produce ethanoic acid. And 2-methyl propane with KMnO4 oxidation, it will produce 2-methyl propan 2-ol. 2-methyl propan 2-ol. So it will be a secondary alcohol. Isomerization. N-alkanes on heating in presence of anhydrous aluminium chloride and hydrogen chloride gas isomerize into branched chain alkanes. The major products are given below. Some minor products are also possible with which we can think over. The minor products are generally not reported in organic reactions. So the reactant is here taken as an alkyl in hexane and anhydrous AlCl3 HCl is given here. So it will isomerize into two compound. One is 2-methyl pentene and another is 3-methyl pentane. Next come to aromatization. Let's take an example of hexane, and it is subjected to Cr2O3, V2O5 or M2O3 in presence of 773 Kelvin temperature with 10 to 20 atm pressure. It will produce benzene by dehydrogenation of hexane. Next come to the reaction with steam. CH4 with steam in presence of nickel, it will produce carbon monoxide and hydrogen. Pyrolysis. Let's take hexane as a reactant and it is subjected to pyrolysis at temperature 773 Kelvin. It will produce three types of compounds: C6H12, C4H8, C3H6, etc. Pyrolysis of alkanes is believed to be a free radical reaction. Preparation of oil, gas or petrol gas from kerosene oil or petrol involve the principle of the pyrolysis. For example, dodecane, a constituent of the kerosene oil, on heating to 973 Kelvin in presence of platinum and palladium or nickel, gives the mixture of the heptane and pentene C12H26 converted into heptane, pentene and other products is given in the reaction. Next come to the conformation of alkanes. Alkanes contain carbon-carbon sigma bonds. Electron distribution of the sigma bond molecular orbital symmetrical around the internuclear axis of the CC bond, which is not distributed due to the rotation of its axis. This permits free rotation about CC single bond. This rotation results into the different spatial arrangements of some spaces which can change into another. Such spatial arrangement of atoms which can be converted into one another rotation around the CC single bond are called conformation. There are conformers or rotamers. The alkanes they have infinite number of the conformation by the rotation around CC single bond. However, it may be remembered that the rotation around the CC single bond is not completely free. It is hindered by a small energy barrier of 1 to 20 kJ per mole due to weak repulsive interaction between the adjacent bond. Such a type of repulsive interaction is called torsional strain. Next come to the conformation of ethane. There are three forms of conformation of ethane. One is eclipsed, one is staggered, and another is skew, which is denoted in Sawhorse and Newman projection. This is Sawhorse projection in the left side, and this is Newman projection in the right side. The first one is eclipsed position, second one is staggered position. Staggered has lowest energy, eclipsed has highest energy. And another form is found for butane, which is gauge form. Next come to isomerism, structural isomerism, where the position of the double bond, of the alkene shifts and the isomers produce. Let's but1 and but2, they are structural isomer with each other. They have same molecular formula, but they are structural isomer. Next come to geometrical isomerism, which is cis-trans isomerism. If two allyl groups are in one side, this is cis isomer, and two allyl groups are in opposite direction, these are trans isomer. Next come to preparation. From alkyne, if we reduce alkyne in presence of palladium charcoal or palladium carbon, there will be produced cis alkene. If we reduce alkyne in presence of sodium with liquid ammonia, it will produce trans alkene. If I can produce ethine in presence of palladium charcoal, it will produce ethene. Then if we reduce propine in presence of palladium carbon, it will produce propene. From alkyl halide we can also prepare alkene by dehydrogenation, that is beta hydrogen elimination reaction. Let's take an example of ethyl halide, and let's take an alcoholic KOH with heat or refluxing condition. It will produce alkene or ethylene gas. Next, taking ethanol as an reactant, and it is subjected to the reflux with concentrated H2SO4. It will produce ethene as a product. Next, there are some transformation we can produce its derivatives. If ethene is subjected to liquid bromine in CCl4, it will produce 1,2-dibromo ethane compound. Propene, if it's subjected to chlorine gas, it will produce 1,2-dichloropropane. This is addition reaction into the ethylene bond. Next, addition of hydrogen halide. The rate of addition of hydrogen halide will be Hi greater than HBr greater than HCl greater than HF. So it will be actually Markovnikov addition. Following the Markovnikov's rule, the halogen atom will be added into the carbonate where the number of hydrogen is less, so which will be the major product. Here the reaction with the propene with the HBr will produce 2-bromopropane as major product. The mechanism is given below. The mechanism involves the formation of the carbocation and the readily attack of the halide ion into the carbon atom, which bears less number of hydrogen. Next, there is anti-Markovnikov addition or peroxide effect or Kharash effect. if HBr addition into propene or unsymmetrical alkene is subjected to HBr addition in presence of peroxide, H2O2 or any peroxide, organic peroxide, then the 1-bromopropane will be the major product. Actually, it will passes through the radical formation mechanism, and which directs the reaction to involve into the radical pathway with the more stable radical formation. So that's why the 1-bromopropane will be the major product in anti-Markovnikov addition of unsymmetrical alkene like propane. The addition of sulfuric acid into ethylene will produce sulfonated compound, and after hydrolysis we can get alcohol from it. Then addition of water can be done in presence of acid, in presence of dilute sulfuric acid. So it will also be added through Markovnikov addition. Number 6, then oxidation reaction of alkene. The oxidation reaction will produce alcohol, that is dilute KMnO4 will produce ethane 1,2-diol. Dilute KMnO4 will produce propane 1,2-diol. The acidic KMnO4 will produce propane 2-one from 2-methyl propene, and from butene acidic KMnO4 will further oxidize the butene into ethanoic acid. Next come to ozonolysis reaction. The double bond will be affected with ozone. There will be formation of first monoozonide, then comes to ozonide, and after giving zinc water into the ozonide compound, it will produce ethanol and methanol as a product. Next come to polymerization reaction. The ethylene molecule can polymerize at high temperature and pressure with presence of catalyst into polythene. Next come to alkynes. Alkyne, simple alkyne is ethyne. It can be produced from calcium carbide. If calcium carbide is subjected to water vapor or water, simple water, it will produce acetylene gas. The structure of the acetylene molecule is given below. There presents triple bond. There is one single carbon bond, and there is two double bond formed with 2py and 2pz orbital overlap. There are some examples given here. One is hexine, second one is hex 2-in, third one is hex 3-in, fourth one is 3-methyl pent 1-ine, next is 4-methyl pent 1-ine, next is 3-dimethyl but 1-ine. From vicinal dihalide we can produce, from vicinal dihalide we can also produce alkyne. So 1,2-dibromoethane, if it is subjected with KOH alcohol, it will form ethane. Properties, physical properties of alkyne follow the same trend of the alkene and alkanes. The first 3 members are gaseous, next 8 are liquid, and higher ones are solid. All alkynes are colorless. Ethane has characteristic odor. Other members are colorless. Alkynes are weakly polar in nature. They are lighter than water and immiscible with the water but soluble in organic solvents like ethers, carbon tetrachloride and benzene. Their melting point, boiling point and density increases with increasing the molecular mass. The chemical properties. Number 1. Acidic character of alkynes. The sodium metal and the sodamide are strong bases. They react with the ethine to form the sodium acetylide. And the liberation of hydrogen gas. These reactions have not been observed in case of ethene or ethane, thus indicating that ethine is more acidic than ethene compound. So the reaction is given below here. These reactions are not shown by alkenes and alkanes, hence used the distinction between the alkyne, alkene and alkyne. What about the above reaction of butane and but1ine and butene? How can we distinguish between? So like this. So alkane, alkenes and alkynes follow the following trend in their acidic nature. Ethine is greater than ethene, greater than ethane. And second one, ethine is greater than propine is greater than butane. Next come to addition of hydrogen. Addition of hydrogen into ethane molecule will produce ethane. In propane molecule will produce propene. The catalyst is here platinum, palladium or nickel. The addition of hydrogen halogens into ethane, it will produce tetrabromo compound, dibromo and tetrabromo compound. The addition of hydrogen halide will produce dibromo compound, dibromo alkane. The addition of water will produce ethanol, aldehyde and ketone in this compound. If we take ethine and take Hg2 plus in presence of H plus in presence of heat, it will first form an enol. And enol will be converted into ethanol by tautomerism, and this tautomerism will produce ethanol, that is aldehyde, and here it will produce propane or propanone, which is a ketonic compound. Next come to the structure of benzene. There is two mesomeric form of the 1,2-dibromobenzene. However, benzene is found to form only orthosubstituted product. This problem was overcome by Kekulé structure. This is the pi bonded structure of the benzene ring. Here vertical p orbitals overlap with each other and forms an electron cloud over the ring, which is pi electron cloud of benzene ring, and this pi electron cloud is responsible for the electrophilic substitution reaction in benzene ring. Rules of aromaticity: planarity, 4n plus 2 pi electron, and complete delocalization of the pi electrons, which is called as Haeckel rule. So Haeckel rule predicts the aromaticity of the compound. There are some examples of the aromatic compound. The benzene is aromatic cyclopentadienyl anion is aromatic. Cycloheptatrienyl cation is aromatic. Next comes naphthalene. Naphthalene is also aromatic. Anthracene is aromatic. Phenanthrene is also aromatic. The formation of benzenoid aromatic compound. From the decarboxylation of the carboxylic acid, we can get benzene. From phenol with zinc and heat, we get benzene, and benzene will react with chlorine in presence of anhydrous AlCl3, will form chlorobenzene. Benzene, if react with concentrated HNO3 and concentrated H2SO4, will form nitrobenzene. The fuming sulfuric acid will form benzene sulfonic acid. The anhydrous AlCl3 will form toluene. The anhydrous AlCl3 will also form ethyl benzene. This is Friedel-Crafts alkylation reaction. Next come to Friedel-Crafts acylation reaction. The acetyl chloride in anhydrous AlCl3 with heat will form acetophenol. If we take acetic anhydride, it will take as anhydride AlCl3, it will form acetophenol as a product. If we take 6 mole of Cl2 in presence of AlCl3 in dark cold condition with benzene, it will form benzene hexachloride. The mechanism of electrophilic reaction is given here. The electrophile will attack into the benzene ring like that wise. It will form the sigma complex first, then it will get aromaticity by releasing one proton from it. So the mechanism is given here. If benzene is subjected with 3 moles of hydrogen in nickel and heat, it will form cyclohexane, an aliphatic ring compound. Under ultraviolet light, the 3 chlorine molecules add to the benzene to produce the benzene hexachloride, BHC, which is a insecticide. Ortho and para-directing groups. The plus groups are always ortho and para-directing groups. So OH group, Cl group, bromine Br group, fluorine group, etc. are ortho and para-directing groups. So the electrophilic substitution will occur mostly in para position and then next in ortho position. The activating groups are NH2, NHR, NHCOCH3, COCH3, CH3, CH2, C2H5, etc. activating groups. In case of aryl halide, the halogens are moderately deactivating because of their strong minus I effect. Meta-directing groups are deactivating groups like NO2, CN, CHO, COR, COOH, CRR, SO3, etc. So the resonance hybrid structure suggesting that there is a generation of positive charge on the ortho and para position. So it is meta-directing group. These are some aromatic compounds, polyaromatic compounds. 1,2-benzanthracene. Next one is 3-methyl cyclolanthrin. Next one is 1,2-benchpyridine. Next one is 1,2,5,6-dibenzene anthracene. Last one is 9,10 dimethyl 1,2 benzene anthracene. Thank you. This is the end of the chapter.